Hello to any sixth formers who might be watching this video. We're going to talk about differentiation from first principles. So the whole idea behind differentiation is that we're essentially looking at finding the gradient of a function at every single point or any single point on the function. So right here we've got a nice quadratic. Doesn't really matter what the equation of it is. It really doesn't matter at all. We know now that we know how to differentiate, we know how to actually find the derivative if we were given the equation of the function. However, if we didn't know the equation of the function and we wanted to use the points that we can see on the graph here, what we'd actually be looking to do is we'd be looking to find the gradient between 2 points that happen to live on this function. So for instance, I'm literally just going to choose any 2 random points, like maybe this one right here and this one over here. And what I could do is I could actually join those two points up with as close to a straight line as possible. I'm sorry, I don't have a ruler on this app. So I could actually go ahead and find the equation of this red line. Now that red line kind of looks very similar to the actual equation of the curve, but it's not exactly the same. I could then go ahead and do that same task again. I'm going to change the color to blue. And I could find the gradient now maybe between this point and this point. And if I join those two lines up, well, that blue line is much, much closer to that actual curve. Now, the reason why this is important is because from GCSE, you know how to find the equation between, you know how to find the equation of the gradient. You don't know how to do that. I'm just making things up. You know how to find the gradient between 2 points. So what we want to do is we want to now use that in our A-level maths to work out the derivative at any point using this first principles. And since we don't know the equation of this curve, nor do we really care to find out, if we just called this curve f of x, we know that this first blue point right here on 1, doesn't really matter that it's on 1, it's just to denote that. We know that that is actually the point x and f of x. All right, and then what we're going to do is this next point, this point over here at 2, again, it doesn't actually matter that it's at 2, we're going to say it's some distance across. We're going to say that to get from here to here, this distance is actually called h. So in order for us to get to that next point, it would actually just be x plus h across, because we started at x and now we're going h more across, and then the y value would be f of x plus h. So now we've essentially got these two coordinates, right, that I've written in blue. And what we're actually doing from first principles is we're trying to find out what is the gradient between these two blue points. So going back to GCSE, we could say the gradient is the change in y divided by the change in x. So I'm going to say f of x plus h, we're going to say that's our y2, minus our y1, f of x, divided by our x plus h, so our x1 minus our x2, which is, or sorry, x, you know what I mean. I don't have to repeat that. So if we just simplify the bottom of the fraction, we end up with f of x plus 2 minus f of x all divided by h. Now, that's the gradient of that blue line. And we said that that blue line was a pretty close estimate to the actual curve. We started out with that red line, which we could actually find the gradient of that red line in the exact same way, and it would basically give us the exact same definition as well as what we've just written in blue. However, the big question with the first principles and where the limit comes from is what happens if we make h so tiny that the 2 points on the graph are essentially right next to each other? Like, what if I chose this point here as x and then this point right here as x plus h, so that the distance between the 2 points was so small that the distance between them was so tiny it was practically 0. Then those 2 points would be so close to each other that they would be a perfect estimate for the gradient at that particular value. So what we end up looking at is the limit as h approaches 0. So as h gets so tiny that the distance between the 2 points is nearly nothing, that they're basically next to each other, we want to find out what's going to happen to the function then. All right, on the next slide, we'll actually look at the the formula, or not the formula, the definition of the derivative from first principles. It would be useful to write it down. It is given in the formula booklet. This is where I took this actual formula from. All right, so going on from, like I said, this is just from the formula booklet. It says if you would like to find the derivative of f of x, you can take the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So that is given to you in the formula booklet. You don't need to memorize it, but it is useful for you to know and be able to recall it. It is important that you write the limit in front of everything. You might think it's completely useless, but it's actually quite an important part of the question. All right, shall we try to go ahead and do one of these questions? I think I've got 3 examples, maybe 4. We'll see. Here we go. All right, here's our first example. Given that f of x is equal to x squared, find the derivative from first principles. So first thing I'm going to do is I'm going to write down the definition of the derivative from first principles. And that says that the derivative of f is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. All right, so again, we've got the limit as h approaches 0. Now we're going to substitute in what we know. So we're going to find f of x plus h. Well, we know that f of x is x squared. So just over here, I've got f of x plus h is going to be x plus h all squared. Now, I'm going to do some writing in the top right-hand side of the page just because I'm not sure if I'm going to be able to fit everything on the one slide. So this is going to be equal to x squared plus 2hx plus h squared. So I'm going to substitute that in, and then also for the second part, I know that f of x is just x squared. So I can substitute both of those into the top of my fraction. So I've got x squared plus 2hx plus h squared minus x squared, all divided by h. So I'm going to go ahead and clean up the top of the fraction. I've got x squared and take away x squared, so those are going to go away. So again, I'm still thinking about the limit as h approaches 0. So I'm thinking what happens as h gets really, really tiny, and I'm left with 2hx plus h squared, all divided by h. Now, I would, at this point in time, factorize out the letter h. Okay, so what's going to happen here is we've got the limit still as h approaches 0. We always want to write that while we still have h's in our function that we're working on, or in our fraction that we're working on. So we factorize out an h from the top, and we're left with 2x plus h, all divided by h. Now, what's going to happen here is we've got an h in the top and h in the bottom. Those are going to cancel each other out. And now I have to think to myself, what's going to happen to 2x plus h as h gets really close to 0. So I'm going to write one more line. I'm going to find out what is the limit as h goes to 0 of 2x plus h. So as h gets really, really so small that it's, like I said, that the distance between the points is practically nothing. As h goes to 0, 2x plus h pretty much ends up being just 2x. So our derivative ends up being 2x. Now notice, this is the first time that I have not written the limit as h approaches 0, and that's because I no longer have an h in my expression. So h is so tiny that I can basically ignore it because it's not going to make an impact on my answer. So there we go, 2x. I also know already, because I know about derivatives, I know that the derivative of x squared is 2x, so I got it correct. And that's what they're looking for. X squared is definitely the nicest one to do. Let's see what else we can get, what other questions we can get. All right, so our next example is the same idea. Given that f of x is 3x this time, find the derivative of x. Find the derivative of f of x from first principles. So this time it's actually even a much nicer function. I'm going to go ahead and start the same way I did before. I'm going to start by writing down my definition of my derivative, and that is the derivative of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. And then again in the corner, I'm going to write what I need to find. So f of x plus h, that is going to be 3 times by x plus h, which is going to be 3x plus 3h. And f of x from the question is just 3x. Now that I know that, I can go ahead and fill both of those in. So I end up with the limit as h approaches 0 of 3x plus 3h minus 3x, all divided by h. So I'm going to clean up the top half of my fraction. 3x minus 3x is going to give us 0, so our derivative is going to become the limit as h approaches 0 of 3h divided by h. I think this time I don't have to factorize. I think it's pretty obvious what's happening here. I can cancel out my h's. H divided by h is going to give me 1. And I'm actually left with no h's at all. So I'm looking for the limit as h approaches 0 of just 3, which is just going to give us 3. There's no h's left to really contend with anything. Also, I can double check the derivative of 3x is 3, so I'm probably headed in the right direction there. And then we're done. And that's it. It might be nice if you write the derivative at the end as well, but there you go. All right, let's find a more complicated version of this question now. All right, we found it. This one's definitely more complicated. Given that f of x is equal to 2x cubed, find the derivative from first principles. Okay, so let's start by writing out our definition. So the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And then I'm going to try to do my working out at the top as well in the interest of space. So f of x plus h is equal to 2 times by x plus h all cubed. So I'm going to try to use what I know about binomial expansion. Let's see if this is a good practice for that. So 2 times by x cubed plus 3hx squared plus 3h squared x plus x cubed. All right, I hope that's right. I think that's right. I'm not going to go and check. I'm just going to leave it at that. And then I'm going to expand that 2 across everything. So I get 2x cubed plus 6hx squared plus 6h squared x plus 2x cubed. All right, and then also we need f of x, which is just 2x cubed. That's always the nice part. Okay, but don't be afraid. You may very well have to expand something like a double bracket with squared, or because you do know about your binomial expansion, they might ask you to expand something that's to the power of 3 or 4. I don't know if I've ever seen them really ask you to expand much more than that, but 3 is pretty standard. All right, so let's go ahead and put this all together. We're looking for the limit as h approaches 0 of 2x cubed plus 6hx squared plus 6h squared x plus 2x cubed. Oh, I made a mistake when I was copying things, and I can't remember that quickly. Sorry, this is a mistake up here, and that's a mistake there. Let's go back and fix that. Sorry, very sorry. So we've got 2h cubed there, and this is also a 2h cubed. So sorry. All right, so there's all of f of x plus h, and then we're going to subtract off our 2x cubed, which is f of x, and then we're going to divide the whole thing by h. All right, let's clean up the top of the fraction. So we are looking for the limit as h approaches 0 of 2x cubed and 2x cubed, different signs, so those are going to get rid of each other. That's great. And then we're left with 6hx squared plus 6h squared x plus 2h cubed, all divided by h. So now I'm going to go ahead and factorize. So this is the limit as h approaches 0 of h times by 6x squared plus 6hx plus 2h squared, all divided by h. So these two h's can cancel each other out, and we are left almost done now with the limit as h approaches 0 of 6x squared plus 6hx plus 2h squared. So we got to think, as h gets really tiny, so it's practically 0. So we now have in this second term right here, we have 6 times practically 0 times by x. Well, if we multiply anything by 0, it's going to be 0. And if we multiply anything by practically 0, we're going to get practically 0. So this is going to go to 0. And the same with 2h squared. So we're going to take practically 0, we're going to square it and then multiply it by 6. I'm fairly certain that that is just going to go towards 0. And if they go towards 0, we don't actually have to consider them because they are so tiny, they're not going to affect anything. So all that's going to be left is the 6x squared, which has no h's in it. So we are left with 6x squared. And knowing what we know about differentiation, we know that 2x cubed, the derivative of that is going to give us 6x squared. So there we go. There's your derivative from first principles. There's 3 different examples. There is a 4th example. I might not talk through it quite as quickly. I might just do it and not say any words. Okay? Here we go. That was a long 2 minutes of silence, but there we go. The only thing that I think would mess people up is this little part right here, and that is because I'm doing take away x squared minus 4x. So if I expand that out, it becomes take away x squared plus 4x. All right, there you go. You've got 4 different versions of this. So just with a single power, or just a single x, you got with x squared, you got with x cubed and with a number in front of it, and you've got x squared minus another value of x. All right, I think that is it for first principles. Do let me know if you have any questions on the Google Classroom. All right, hope that was helpful, and I will talk to you later. Bye.